Where did that? We talked about the weird things last time. Sure, let's turn this on. It's weird. Just a reminder, I'm sure you've been made aware, but there is no class tomorrow. It's Veterans Day, so don't come to school. You won't be here. Um, yeah, like maybe what am I actually doing? Nope, not you. There we go. So the sure. All right. Yeah, I guess we should talk about that. So we're gonna move on to chapter 14 stuff, which is talking about multivariable functions, specifically functions of two variables. So like g- talking about kind of graphing surfaces and all sorts of interesting things that go along with that. So let's write down some stuff here. I'm gonna need more paper. Let's see. Co-21C. Today is the 10th of November. Chapter 14. And that's not what I want. I want paper in here. That's not paper, paper, paper. One is yeah, it's plenty. So we'll talk about some of the quadric surfaces and what they kind of look like, but honestly, you probably don't do a whole lot of actual graphing of three-dimensional surfaces in this class. I would say what you're more typically responsible for is knowing what equations have what shape in 3D space. So that's what we'll kind of focus on for a little bit here. And then we'll quickly move on to talking about limits and then eventually partial derivatives, which is probably what you actually mostly need this chapter for, which also is probably the easiest part. Like all of you with very minimal instruction could take a partial derivative almost immediately. Like it's the easiest part of the chapter completely. So when we get there, it'll be like no problem. But the buildup is a little bit so, and we do have to talk about the limits because I'm sure that whichever class is the class that's all proof happy, I'm sure he's going to have you prove that a limit is equal to something, which is a giant pain, especially these ones. Yeah. So, but we'll get there. So, but let's talk about graphing some stuff. So let's graph the function f of xy equal to x squared plus y squared. And I'll just point out that just like back when we graphed functions in two dimensions, like so, back when you might have graphed something like f of x equal to x squared, we often think of f of x as y. And in a similar way, we're going to think of f of xy as z. Same idea. So there's lots of ways to do this. A couple ways to think about this is one thing we often do, and again, I'll point out, no, I won't put that out. I need a black pen though. We're going to think about the traces for a second. So the traces are what's happening in kind of each of the coordinate planes. So what's happening in the XY plane, the XZ plane, and the YZ plane. So in the in the XY plane, not a lot's happening. In the XY plane, we're going to set z equal to 0. And if z is 0, you've got 0 equal to x squared plus y squared. And there's literally only one point that satisfies that equation, the origin. So not very exciting. Your trace is the point 0, 0. Kind of boring. In fact, let's be a little bit, yeah. In the XZ plane, and if you might have already noticed, but whichever plane you're in, the missing variable is equal to 0, right? If you're on the floor, Z is 0. If you're on the back wall, X is 0. If you're on the side wall, Y is 0. So in the XZ plane, Y is 0. And our equation is going to be Z equal to X squared. We know what that looks like. It's just kind of a typical parabola, except we're labeling the y-axis as z instead of as y. So it looks like this. Here's x, here's z, usual parabola. And very similarly, in the yz plane, we literally have the same shape. You have x equal to 0, you're getting z equal to y squared, and same parabola shape in your yz plane. The traces can be helpful. So I would say you can kind of imagine on the YZ plane, you've got a parabola doing this. Might want to look at me for a second. In the XZ plane, you've got a parabola doing this. So you're kind of trying to superimpose those two parabolas that are perpendicular to each other on the same three-dimensional coordinate axis system to get the shape we're looking at. But what is also really helpful is to look at the level curves or the contours. So if you've ever looked at like a topographical map, where you have like the little different lines representing different elevations. That is exactly the idea of what we're doing here. When you talk about level curves, you're just talking about a curve that's always at the same elevation or height. So we might look at level curves setting. Now, you don't really want to do this the long way. You could say, let's set z equal to 1 and see what we've got, or z equal to 2, or z equal to 3. And you could, right? If you set z equal to 1, we'll just do this the long way for a hot minute. You're going to get x squared plus y squared equal to 1, a circle of radius 1. And we set z equal to 2, you're going to get x squared plus y squared equal to 2, a circle of radius square root of 2. But more generally, what you usually do is say, I'm just going to pick c as my height or my elevation. So at elevation C, or maybe even elevation Z equal to C, we're going to get x squared plus y squared equal to C. And that's obviously a circle centered at the origin, and the radius is equal to the square root of C. Yeah, correct. A constant that is in the range of the function. Say it one more time. Like why am I only doing it for Z? Because typically, not always, but typically we're thinking of Z as a function of the two inputs X and Y. And so we're kind of, and again, this is not always the case. Like sometimes it makes much more sense to think of the level curves instead of being parallel to the ground, the XY plane. Sometimes it makes more sense to think of them parallel to the YZ plane or to the XZ plane. But a lot of the times to be parallel to the XY. But it's more of a skill we develop with experience. So like, which plane do I actually want to pick to think about the level curves on? Usually parallel to the ground to the XY plane, but not always. So graphing this, yeah, we do want to do it this way. So I'm going to draw my traces. So in the X, Y, Z, in the YZ plane, which is always the plane I would choose to start graphing the first because it is the one that is on the piece of paper, I'm just going to draw a usual parabola as best I can. But then in the XZ plane, slicing out towards you, I'm also going to draw a parabola, but now it's going to be, like tilted. So it's going to have less. So it's going to look, more like this. And then pens. At different elevations, like say at a height of 1, we have a circle of radius 1. And at a height of, let's be smart about this, let's say 1, 2, 3, 4. At a height of 4, we have a circle of radius 2. And you could draw the level curves in the middle if you really wanted to. But once you've drawn a couple of them, you're like, okay, I get the idea. Like my level curves are circles. Remind me, is anyone using web work? Good. Not that I have a problem with, just that the kinds of questions they ask for these questions are super annoying. Like it's like for this function, describe the level curves, and it's like the level curves are concentric circles that are equally spaced apart or not equally spaced apart, and it's just kind of annoying to describe. These ones would be not equally spaced apart because if you go up one, your radius isn't increasing by the same amount every time. The radius is not a linear function of the height. As you can see, right? The radius is the square root of the height. This is called a paraboloid. Unlike a parabolic cylinder that we talked about a class or two ago. So this is a paraboloid. Paraboloid, sure, it's probably spelled close to that. And it's one of your 6 or 7 quadric surfaces. I saw someone wrote, I do believe they are called quadric, not quadratic surfaces. Although I did some Googling and apparently either label is technically correct, but I've always been told quadratic is not correct. So whatever. Anyway, these are quadric surfaces. Quadric surfaces. Not quadratic. Even if your instructor said quadratic. But don't fight them on it. So let's see what else we're looking at. So yeah, we're just gonna we're gonna go through the highlights here, the important ones, and then we'll talk about kind of how they might differ. So I'll point out for a paraboloid, basically the thing that's to the first power is the axis of symmetry. So if you had x equal to z squared plus y squared, it would be a paraboloid opening up along the x-axis out towards you. Or if you had y equal to x squared plus z squared, your paraboloid would open to the right. Or if you had y equal to negative x squared minus z squared, your paraboloid would open to the left. And then you can make it even more interesting by varying the coefficients of x and y. So if it was like 2x squared plus 3y squared, it would be an elliptic paraboloid, right? Because your level curves would no longer be circles, they'd be ellipses. All of this is described in some detail in the textbook. Like, in fact, there's like a whole page in the textbook where they talk about like all 6 or 7 quadric surfaces and what they kind of look like and what their general formulas are. Question? Okay. So let's look at the next couple ones. Yeah, and there's no particular rhyme or reason or order to the order I'm presenting them in. I'm just presenting them in the order I'm thinking of them in, really. So, or the order that I'm better at drawing them in, maybe. So the next one is, let's look at the classic. Sure. Oh, this one's super fun. Let's look at z equal to y squared minus x squared. And I would say, typically when we're drawing these, we usually think of drawing them or writing them where z is a function of x or y, x and y, although not always. So this you could also think of as f of x comma y equal to y squared minus x squared. And let's look at the typical things. We'll be a little bit more let's look at our plane and our trace first of all. So in the x equals 0 plane, let's not do z equals 0 yet. If x is 0, you get your nice z equal to y squared, your upward opening parabola. In your y equals 0 plane, you're going to get z equal to negative x squared, your downward opening parabola. And then, kind of annoyingly, in the xy plane where z is equal to 0, you're going to get 0 equal to y squared minus x squared. Which, if you solve for y, you get y squared equal to x squared. And you don't exactly get y equal to x, you get y equal to plus or minus x. Or essentially, no, that's it. Really, if you square both sides, you really get the absolute value of y equal to the absolute value of x. So you get an x as your graph, literally the upward and the downward opening absolute value functions. Yeah. Oh, because I really what I did was I brought x squared to the other side and then I just rearranged the order of it because I don't really care which side things are on. Right, but right, I brought y squared over and then multiplied both sides by -1. I skipped a step. Um, and then if we look at our our level curves for our level curves. So if we set z equal to say 1, well, we get 1 equal to y squared minus x squared. And this might not feel like a familiar graph. It's a hyperbola. So yeah, I know, right? So now the question is, how much do we really need to know this? And the answer is, I don't really know how much we actually need to know this. But here's what it looks like. So this graph looks like the following. So you all know the graph very well of one hyperbola. It's just rotated in an atypical way. So the graph of y equals 1 over x is a hyperbola. So is this graph here. So when I graph this, let's see, if x is 0, my y-intercepts are plus or minus 1. And then this graph has some slant asymptotes at y equal to x and y equal to negative x. So here's what this hyperbola looks like. Kind of like that. And now imagine for a second, you rotated that graph 45 degrees clockwise. It would look exactly like the graph of y equals 1 over x. See? Right? Like it really does. So y equals 1 over x is a hyperbola as well. What makes a hyperbola is basically there's these two little points called the focuses, or the plural of that is actually foci. And every point on your graph, the distance from one foci and the distance from the other foci, the difference between them is always the same number. So whether it's this point here or this point here or this point here, the difference of those two distances is always the same. There's like all these really weird kind of geometric ways of describing like an ellipse or a parabola or a hyperbola being like the difference or the sum of the distances between a couple things. Kind of cool. Important, not that important. So I'll point out the higher you go, right? So for example, if z was equal to 2, your hyperbola would just move a little further up. Or if z was equal to, let's say z was equal to 4, 4 equal to y squared minus x squared, your hyperbola, now you'd have a y-intercept of 2 and a negative 2, and it would look kind of like this. Not great at drawing them. On the other hand, if z, oh, question, yeah. On the other hand, if z was equal to -1, then we'd have -1 equal to y squared minus x squared, or multiplying everything by -1, +1 equal to x squared minus y squared, and then the intercepts would be x equal to +1 and -1. Now, to answer a previous question, I will say for this one, it also does kind of make sense to think about level curves in the different directions. But they're not that hard to think about because here, if you say, right, if you let, say, x equal 1, right, say x is equal to, let's actually say plus or minus 1, you're going to get z equal to y squared minus 1. So it's just going to shift your parabola down by 1 if you move in the x direction. And similarly, if you were to set y equal to plus or minus 1, you're going to get z equal to 1 minus x squared. So you're shifting your downward opening parabola up 1. Okay, so the hard part about this is all this information doesn't make it easier to graph this thing. It's useful to know it's useful if you're being asked about it. It really is the actual truth. But graphing this thing, here's what I'm gonna do. So yeah. The usual XYZ coordinate system. So let's talk about what's important here. My trace in the x direction in the YZ plane and the XZ plane. I would not recommend at all drawing the thing I didn't even draw, the X shape in the XY plane. Like that is not helpful at all. But we're going to look at it in 3 dimensions second. So I'm going to draw my upward opening parabola in the YZ plane in blue. And my downward opening parabola in the XZ plane. And then if you wanted to, you could draw more downward. So like if y is equal to plus or minus 1, my downward opening parabola is a little higher up now. So it's kind of like this. Or like this. Or if x is equal to plus or minus 1, my this is where my graph starts to get like I'm about to like fall apart here. Right. Yeah, that so like okay, I'm gonna try and draw it. If x is equal to 1, my upward opening parabola has moved down a bit, so it's kind of like it's right there. Kind of. It's not the best picture of drawing ever. You can kind of see it starting to come together. But really what I should do is say, here's my hyperbolas that go this way, and my hyperbolas that come out this way. And then we kind of attach it all like this. Kind of looks like a big old bat or something. The saddle, which is kind of fun to draw. I'm not gonna lie. Like I like drawing, so even though it kind of started to fall apart. But you know what you have that's way better than my drawings is Desmos 3D. And you know what it's really useful for is looking at things that are hard to draw, or not even that hard to draw, but still, like you can only do so much. So that's not the right Desmos. That's Desmos 2D there, though. That's not 3D. So you can actually graph this really easily. Z equal to y squared minus x squared. And there it is. And you can even see the trace right there in the XY plane, right? You can see that. You can be smart about it and do that. And you can see, oh yeah, look, there's your y equals x and your y equals negative x. And you can also, if you want to see some of the other level curves, you can just say like set like z equal to 3. And oh yeah, look, there's your hyperbola. Or if you set z equal to negative 3. And turn this one off. There's your other hyperbola going the other way. Kind of harder to see from this side though, right? But that's not what I meant to do. Right? You can kind of see, oops, stop moving around like that. Anyway, there you go. Right there it is right there. And you can even do that, like you can kind of look at level curves in any direction you want. You can set, that's not the one I wanted to do. You could set x equal to 3. That might be too big. Yeah. How about x equal to 1? I turned it off. That's the problem. Yeah, extend that, please. Now you can see, oh yeah, there's your parabola shape. It's shifted down. Let me zoom out a bit. There's your parabola shape, right? But we shifted down because we moved out. Or if you set y equal to 2, right? There's your other parabola shape. But again, move down. So you can see a lot of things if you want to. Okay, so let's talk about the rest. Oh yeah, question. Because like because it's hard. Like it's like so if you look at the shape here, like there is a basically what's happening here is on this curvy surface, there's this line that's on the floor that's always touching the surface, but it's still also in the XY plane. And for me, it just like we can let's draw it. So let's go back to the thing. So if I turn those off for a second, so check this out. If we draw the line y equal to x, just to draw one of the two. Oops, that's not. There we go. So look at this line here. It's hard as a human being to draw that line tangent to this surface that is has all over the place vertically, but that part's always in just the xy plane. And also you can of course draw the line y equal to negative x. So it's not in red. That's a stupid choice. Why would you choose red? Okay. Right. They're not easy to draw. Really, is really the truth. Okay, so let's talk about the rest of the quadric surfaces, and then we'll see what we have else to say. So yeah, no, you're good. Uh-huh. Yeah, you're right. So if I was asked to draw, if I probably should say, yeah, my in my XY plane, it would look like that. Yeah. Um, so I would say let's write down the rest of them relatively quickly here. So there's kind of one more, yeah, there's one more what I would say is an odd man out, and then the last three kind of all have a similar format. So the other one here is z squared equal to x squared plus y squared. And this one's kind of funky because it's not actually a function of x and y. So in the previous examples, plural, you could say they pass an analog of the vertical line test. If you drew any vertical line in three-dimensional space, it would only puncture your surface in one point. That is not going to be true here. This is a double cone, also known as a cone. So this is, well, again, not a whole lot happening in the XY plane because if you set z equal to 0, you're going to get x equal to 0 and y equal to 0. That's the only option. But in the other two planes, in the x equals 0 plane, oh, look, we're getting z squared equal to y squared. It's those two lines that make an x again. And how fun. So that's what we get in the yz plane. And if we set y equal to 0, we get z squared equal to x squared, which is also the same shape, which I don't need to draw again. And then our level curves are also going to be circles here. So if we set the elevation to be z equal to c, then we're exactly going to get x squared plus y squared equal to c squared, a circle of radius c, centered at the origin, of course. And unlike the paraboloid, these circles are equally spaced out. If I start drawing some of them, if I start drawing my level curves, well, if c is equal to 1, the radius is 1. So there's my level curve and elevation of 1. And if c is equal to 2, the radius is 2. And so on and so on and so on. So here, my graph looks like the following. So here are my level curves, or my traces, which are going to look kind of dumb for a second. So here's my z equals negative y, my z equals y traces. Oosh, can I draw this straight enough? And then, yeah, okay, good job. I'm gonna be smart. I'm not gonna draw the x ones. I know that level curves are circles, so let's just draw some circles. Same thing on the bottom here. If you wanted to draw the x, the The XZ trace, you could try. I'm just not good at it. It's kind of like coming up that way and going back that way and coming up this way and going back that way. And if you wanted it to be a function, the top half would just be z equal to the square root of x squared plus y squared. And then just like I said before, if instead it was the x squared isolated, this cone would open along the x-axis. And if it was the y squared isolated, the cone would open on the y-axis. Another way to think of this, by the way, is x squared plus y squared minus z squared equal to 0. So in this equation, and in general, when I think about these ones where they're all squares, the odd man out is the axis you're opening on. So in this equation, since it's positive x squared plus y squared minus z squared, you're opening along the z-axis. But if it was x squared minus y squared plus z squared equal to 0, we'd be opening along the y-axis. That is going to hold for the next two things we talked about as well. Yeah, okay, so let's look at the next two. So first, so I'll point out, just like the previous one, these next three things we're going to graph are not functions of x and y. They all fail the vertical line test, for lack of a better word. Let's say this next one is, which one do I want? Yeah, sure. Yeah, x squared plus y squared minus z squared equal to 4. I don't remember which one this is, to be honest, but we're going to figure it out by looking at the traces. So if z is equal to 0, we've got a nice trace. We've got x squared plus y squared equal to 4. Circle of radius 2. And fun times, if y is equal to 0, we have x squared minus z squared equal to 4, which is another hyperbola. Hyperbola, it's going to be having its intercepts on the x-axis. So it's going to look vaguely like this. And as you've seen with many of these already, what happens in one trace often happens the same way in the other trace. If z is equal to 0, sorry, not z is equal to 0. If x is equal to 0, you're going to get y squared minus z squared equal to 4. And the same sort of hyperbolic shape, which I'm not very good at drawing, as you might have noticed. And then if you let z be a larger value or a different value, you're going to get bigger circles, right? For example, if z is equal to c, we get x squared plus y squared minus c squared equal to 4, or x squared plus y squared equal to 4 plus c squared. That's going to be a circle with a radius of the square root of 4 plus c squared. So a larger circle as you go higher up or lower down, because you're just squaring z. So it doesn't matter if z is positive or negative. So as we move up or down, our circles widen out, which again makes some sense if you try to think about what's happening here, in that here's what our graph is going to look like. Okay, again, I'm going to follow my own advice. I'm going to deal with what's happening in the YZ plane and maybe the XY plane, but I'm going to try to really kind of ignore the XZ plane because it's the one that's hardest for me to draw in. So in my XY plane, good stuff here. I've got a circle of radius 2. Not too terrible. And then in my YZ plane, I've got my hyperbola looking like this. So basically, I'm going to be going kind of out like that, out like that. Same deal over on the left side. Let's try to make this look symmetric. if we can. Not so great there. Kind of jinxed myself by saying it. Yeah, well, that's kind of ugly. Sorry about that. But it should be symmetric. And then we know that, as we just said, as we go higher up or lower down, our level curves that are circles have a larger radius. So like if we go up a little bit, larger radius, up further, larger radius, or down further, larger radius. This is called a hyperboloid of one sheet because your traces are hyperbolas and your surface is all one surface. Unlike the next one we draw, where the surface is actually two distinct surfaces. So I would point out in this one, just like the last one, as is typical the way we've chosen to do this, Z is the odd man out, and the hyperboloid of one sheet opens along the Z-axis, or is symmetrical around the Z-axis, if you want to think about it that way. The next one's going to look almost the same. Now, I could do this really annoyingly, and I will to make a point. So we'll start off with this. I'm going to say it's x squared plus y squared minus z squared equal to -4. But a more typical way of writing this would be something like -x squared minus y squared plus z squared equal to 4, or maybe z squared equal to 4 plus x squared plus y squared. All these are the same equation. To me, I prefer to write it in this kind of standard way. Why do I think that this is standard? I'm thinking this is standard because my X, Y, and Z are all in lexicographic order, or alphabetical order, if you want to say it in a non-mathematical way. The lexicographic is the mathy way of saying alphabetical. And it's equal to a positive, or I should say, non-negative constant. If I write it this way, and I see that I have two negative signs, I'm like, cool, hyperboloid of two sheets. If I write it in the standard way, and I see this equation, I'm like, ooh, one negative sign, hyperboloid of one sheet. I find that helpful personally. So here's what I should actually be saying. Oh, I just thought something cool. So sorry. So what I should really be saying here is, let me hold on for 1 second. I'll say the cool thing in a moment. Moderately cool. So this one, same idea. We're going to find our traces. So here, the XY trace is kind of a bummer. You don't have one. X squared plus y squared equal to -4. Nope, not going to have a circle with a radius of imaginary units. No trace in the XY plane. But in the other two planes, we do have traces. For y equal to 0, we have x squared minus z squared equal to -4. Or if you prefer, z squared minus x squared equal to +4. But that tells me it's a hyperbola, but now instead of opening on the x-axis, it's opening on the z-axis. So this one looks like this. There's x, there's z, and my z-intercepts are +2 and -2. So kind of like that. And same deal if I let x equal 0. If x equals 0, I get y squared minus z squared. I'm I'm slightly annoyed with myself because I really wanted to be writing it like this, but oh well, I didn't. It's not a huge crime, but I feel kind of bad about it because I made a big deal about how this is the way you should do it, and then was using this over here. So here I get z squared minus y squared equal to 4. So literally the same shape where it's my y-axis here, my z-axis here. So still a hyperbola like this. And we can see that, well, in fact, if our z values are big enough, right? So if our z values are 2 or higher or lower than -2, it's like, for example, if z was equal to 3, let's say plus or minus 3, then I'd have x squared plus y squared minus 3 squared equal to -4, and you add the 9 to both sides, you do get a circle of radius square root of 5 in this case. So our level curves are still circles as long as we go high enough up or low enough down. So let's take a look. Putting it all together. Okay, so all right, so I'm going to try and draw my YZ hyperbola here. So it's doing the usual kind of hyperbola thing. I feel like I don't draw my hyperbolas exaggerated enough. Like the curve should probably be stronger than I'm drawing it, but it's one of those things we don't practice drawing enough, I feel like. It's not a parabola, although it kind of has a parabola-ish vibe, but parabolas don't have slant asymptotes, and hyperbolas do. And then same thing on the other side, looking down like that ish. Okay. I don't really want to draw the one in the XZ direction, but what I do want to draw is some of these level curves. So if I go up a little bit here, right, I have circles that are level curves. Or if I go down far enough. And then at this point, you could try to draw the other hyperbola, which kind of does this deal here. Like that. Or the one down here, trying to move in a direction parallel to the x-axis. Like that. And I kind of think of these as like two satellite dishes opening away from each other. Okay, here's the thing I think is cool, but might not be that cool. Both these hyperboloids of either one sheet or two sheet, it's just kind of a deformation of the cone, the double cone. So the idea basically is if you make this number over here positive, you're kind of pulling the cone out away in the XY direction like this. Whereas if you make that number negative, you're kind of pulling the cone away from the XY plane like this, either into hyperboloid of two sheets or hyperboloid of one sheet. Kind of a neat idea. It's probably easier to see if you look at Desmos. Shocking, I know. So if we look back at our, ooh, come on, cursor. Yeah. So yeah, let's delete all the things. Can I delete all the things? Maybe. So here's your nice, lovely cone, z squared equal to x squared plus y squared, or negative x squared. Let's see how this works out. Minus y squared plus z squared equal to 0. Yeah. There's your good old double cone. But then if you just say, add a little, oh look, hyperboloid of two sheets. Or if you make it negative, hyperboloid of one sheet. It's just kind of deforming a little bit away from whichever thing it is. I think that's kind of neat. Like maybe I'm wrong, but it's kind of cool. So anyway, you can kind of see how all three of those quadric surfaces are kind of related to each other and also pretty much have the same equation, right? They're literally all the same equation, just equal to a different constant, either a positive constant, a negative constant, or a 0 when you kind of have everything coming down to one point. So kind of cool. And finally, the last quadric surface, the sphere, or more generally, the ellipsoid. So that one's probably the easiest of all three. It's where everything is positive. So for example, something like x squared plus y squared over 4 plus z squared over 9 equal to 1. The kind of general way of writing the equation is having coefficients of x squared, y squared, and z squared all equal to 1. But you could totally multiply both sides of this equation by like 36 and write it as 36x squared plus 9y squared plus 4z squared equal to 36. But the hallmark of the ellipsoid is that you have x squared, y squared, z squared, and all of their coefficients are positive. Whereas in the previous ones, one or two of the coefficients have been negative. And this one's probably the easiest to draw. It's just going to look kind of like an egg. Notice how I'm not even drawing the traces because I decided not to. My x-intercepts are plus or minus 1. My y-intercepts are plus or minus 2. And my z-intercepts are plus or minus 3. My trace in the XY plane is the ellipse that goes through those points. My trace in the YZ plane is also the ellipse that goes through the intercepts where at Z is plus or minus 3 and Y is plus or minus 2. Nope, come on, James, you can make this happen. Oof, it's a little eggier than I meant it to look. And finally, my trace in the XZ plane is where X intercepts are 1 and Z intercepts are 3. This is an ellipsoid. And those are your quadric surfaces. How well do you actually need to know them? Probably not that well. That said, they're not the only surfaces that exist, right? You could literally graph lots of other things that are maybe more interesting. I would say the important idea here is really I think the level curves are probably the most important idea of what we've talked about so far. So in the last couple minutes I have here, I'll point out something like, for example, if we looked at the function, sure, f of x comma y equal to 1 over the square root of x squared plus y squared minus 1. Well, it wasn't so much an issue for the other ones we looked at, but this function definitely has some domain restrictions. Here, we start talking about the domain. Before we even talk about anything else, we might say, well, look, the inside of that radical better be not just non-negative, actually strictly greater than 0, because if it was equal to 0, we'd be divided by 0. So this is going to be greater than 0, which means our domain is x squared plus y squared is greater than 1. I'm thinking about the fact that I know that the graph of x squared plus y squared equal to 1 is a circle of radius 1, which I don't want to include in my domain. So I was going to draw my domain, which is some subset of the xy plane. I'm going to draw the circle of radius 1. And since I know I don't want to include it, I'm going to draw it dashed, just like we would draw a dashed line if we didn't want to actually include that boundary. So now here's the question. What points are in my domain here? Are the points inside the circle in my domain? Well, let's check. If I check the point 0, 0, does the point 0, 0 satisfy the inequality? And the verdict is no, it does not. So here's what's nice about this. If you pick a point on one side of your boundary for your domain, and that point is a member, then all the points on that side are. And if it's not, it's all the points on the other side. So alternatively, you could have picked the point, say like 2, 0, and asked, does 2, 0 satisfy it? And the answer is for sure, yes. 2 squared plus 0 squared is 4, which is bigger than 1. So once you know that one point is in your domain, all of the points on that side of the boundary are also in your domain. So domain for these functions is a little bit weirder. It's not an interval. It's an area in the xy plane. It's some set of infinite number of points. So here, the best way to find your domain for functions like this is actually just to draw it. But if someone actually asked you to write what the domain was, it's super kind of annoying. The domain here is the set containing all points x comma y such that x squared plus y squared is bigger than 1. There's no easier way of writing it. So for functions of two variables, your domain is a set of points in the xy plane or the R2 plane. The range, on the other hand, is still kind of typical. The range is how big can your function be, how small can your function be? Well, since we're almost out of time, I'm just going to answer the question here. So this function, the denominator can get really, really big, right? Like super big. So you can make the denominator really big, which make the fraction really, 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 really small, but not quite 0. So your domain goes as low as, your range goes as low as almost 0. And it also gets really, really big. Because if you can make this denominator very, 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 very small. If you pick x equal to 1 and y equal to 0.00, lots of zeros, 1, that denominator is going to be super small. And then when you divide by that super small number, your fraction is going to blow up. So your range here is everything from 0 to infinity. And I guess we'll talk about the rest next time because we're out of time. And then we'll start talking about limits, which for the most part, no, that's not true. For some part, kind of follow the same rules as limits from before. In that whenever you're trying to find a limit, the first thing you should do is plug in whatever x and y are approaching. And then when you get 0 over 0, there's a whole new thing we're going to do, which is actually not that bad. As long as the limit doesn't exist. If the limit exists, then it's kind of not so fun. But we'll tackle that when we get to it. On Wednesday, probably. Thank you. Appreciate it. Oh, that's all right. You can say it's good.